You know, there's this invisible battle happening all around us every single day. It's this constant war between the unbelievable power of the wind and the buildings we live and work in. We're going to pull back the curtain on the hidden engineering that makes sure our buildings win and our cities stand tall.
I mean, you've probably wondered about this, right? You see some massive skyscraper swaying in a crazy storm, and you just think, how on earth is that thing still standing? Well, the answer isn't just about being heavy. It's a masterpiece of some incredibly precise engineering.
So before we can really get into how buildings fight back, we need to understand what they're up against. And believe me, it's a lot more complex than just air that's moving.
Okay, so think big picture for a second. The sun blasts the equator with way more heat than it does the poles. That creates these huge differences in temperature and pressure. Now, you add in the spin of the Earth, and suddenly you get these massive, predictable wind systems that circle the globe.
But see, when that giant global wind system hits a city, oh man, it just turns into chaos. Engineers can't just clock its speed. They have to think about the building's shape, the texture of its glass or concrete, all the other buildings and trees whipping up turbulence around it, and even how dense the air is on that particular day. All right, let's zoom in from that global view right down to the local level and see what actually happens at that exact moment of impact, when the wind slams into a building.
Okay, so here's something most of us never even think about. Wind doesn't just push on a building from the outside. If a window shatters or a door gets blown open, that force gets inside and creates this enormous internal pressure. It's kind of like blowing up a paper bag until it pops. The building is suddenly being attacked from the outside and the inside at the same time. It's a two-front war.
And because it's so complex, engineers have to look at the wind on three totally different levels. First, there's the building as a whole. Is it going to tip over? Second, they look at the big pieces, like individual walls and the roof. And finally, they zoom all the way in on the cladding, every single window, every single panel, to make sure it doesn't get peeled right off.
So how do they figure all this out? It is definitely not guesswork. They have this precise toolkit, basically a formula, that lets them calculate the exact wind force any building on any site is going to have to deal with.
The core idea here is actually pretty simple. Engineers start with a basic wind speed for the whole region. Then they use a series of multipliers, these special factors for things like hills, nearby buildings, and even how important the building is, to cook up a custom wind speed for that one specific building. Let's break down what those factors actually are.
First up, you've got VB, the basic wind speed. Think of this as your starting ingredient. It's a baseline number pulled from years of historical data for that area, and it represents the fastest 3-second gust you'd expect to see in a wide-open field, about 10 meters off the ground.
Next is S1, the topography factor, and this makes total sense when you think about it. The wind doesn't just flow smoothly over the ground. If you build a house on a big hill or right on the edge of a cliff, that wind is going to speed up as it goes over the top. So this factor adjusts our baseline speed for the shape of the land itself.
Then we have S2, the terrain factor. This one's all about ground roughness. And here's where it gets a little counterintuitive. Wind blowing over a flat, open field is going to be much faster near the ground than wind that has to fight its way through a dense city packed with other buildings. All those obstacles create drag and turbulence, and they actually slow the wind down.
And finally, we get to my favorite one, risk. Engineers literally ask, how big of a disaster would it be if this building failed? A temporary shed for a construction site, well, that's not built to the same standard as an office building. And a hospital, which has to stay standing during a catastrophe, that's built to an even higher standard, designed to handle storms that might only show up once a century.
So we've got the theory down. Let's make this real. Let's see how this all comes together with a practical example, one taken right out of an engineering handbook. All right, so here's our guinea pig. A simple, single-story industrial shed. Our job is to figure out the specific design wind speed for this exact structure, on this exact spot.
First things first, we look up the regional data. The basic wind speed, our VB, for this location is 47 meters per second. That's our starting number, our baseline.
Next, we adjust for the terrain. Now, this site isn't some wide-open field. There are other buildings and stuff nearby. That ground roughness actually slows the wind, so we get to multiply our speed by a reduction factor of 0.74. And since the land is pretty flat, our topography factor is just 1. No change there.
And what about the risk? Well, this is a standard industrial shed, a general building with a 50-year expected life, so our risk factor, S3, is exactly 1.0. We're not trying to make it any more or less tough than normal.
So, we crunch the numbers. We take our raw speed of 47 meters per second and multiply it by all our factors. And look at that. Our final design wind speed is 34.78 meters per second. Notice how much the surrounding terrain dropped the force the building actually needs to handle. We've gone from a generic regional number to a super specific value engineers can actually build with.
But hold on, that final number isn't just about pushing on the front wall. It's way more complicated. Think about an airplane wing, right? As air rushes over the curved top, it speeds up and creates lift. Well, the same thing happens to a building. The wind pushes on the front, sure, but it also creates this powerful suction, this negative pressure on the sides and especially on the roof, literally trying to pull the building apart. Every single one of those forces has to be calculated and designed for.
You know, it might feel like we've just been looking at a bunch of math and formulas, but this whole process, it's like a silent guardian that watches over pretty much every single structure we build.
And here's how they bring it all home. That wind speed we just calculated gets converted into pressure, pounds per square inch. Engineers then multiply that pressure by the entire area of a wall or a roof to find the total crushing force that the structure absolutely must be able to resist. It's how abstract numbers become a real-world defense.
And really, that's what this is all about. That is the engineering you can't see. Every single one of these factors, from the spin of our planet to the roughness of the ground to just how important a building is a critical piece of a puzzle that, when it's solved correctly, keeps all of us safe.
We've seen the incredible, meticulous work that goes into designing for the forces we can predict from the past, but it leaves us with this really critical question for the future. As our climate changes, how do we adapt this amazing engineering for a world with storms that might be stronger than anything our risk models have ever seen before?